So will it be live streamed?
Yeah, I just launched it now. It's going to be live streamed in a few seconds. So yeah, if you want to say something, it's going to be on YouTube.
Will it be live streamed?
Yeah, I just launched it now. It's going to be live streamed.
Okay.
That's the proof, unintentionally.
Okay, got it.
Turn your video off if it's too much.
Okay, so I think there are probably be other people joining, but we can start. So that's the third episode of this series on semi-supervised learning and contrastive learning at Stanford. And today we'll have Soumick from Magdeburg in Germany, who is going to present semi-supervised segmentation for brain MRI. Yeah.
Thank you so much. Yeah, thanks. First of all, thanks for the invitation. And I'll first share my screen. Yeah, can you see my screen?
Yep.
Okay, so our paper that I'm going to present today is called DS6, Deformation-aware Semi-supervised Learning, Application to Small Vessel Segmentation with Noisy Training Data. The name DS6 pays homage to Deep Space Nine, Star Trek Deep Space Nine, known as DS9. And here it's deformation-aware segmentation with 6 volumes, hence DS6. So let's start by understanding what we are doing here. Small vessels in brain, such as LSA, are the terminal branches of the arterial vascular tree and is responsible to supply blood to basal ganglia and other places. Pathology of these small vessels can be associated with different diseases, like it can be associated with aging, dementia, Alzheimer's disease. Segmentation and quantification of such vessels is crucial to study cerebral small vessel diseases and other diseases. With the advancements in 7 Tesla MRI, we can capture the small vessels better. Here on the right, you can see one example of one volume where we can see really minute and really small vessels, which are 1 to 2 voxels in diameter. And our goal here is to be able to segment them automatically. Now, what are the challenges in general? We can do manual segmentation. That's, of course, an option always. And they are reliable, but they can be really time consuming and really hectic to do it properly. We have semi-automated techniques, but there also we need to do manual parameter tuning for every data sets. But then there's, of course, deep learning and non-deep learning techniques. With non-deep learning techniques like Frangi or MSFDF pipeline, we can capture vessels and we can segment small and medium to large vessels quite nicely. But for small vessels, it can be really challenging. There are deep learning techniques which can do this job nicely, but usually deep learning techniques come with this need of larger training data sets. Now, for just to give you a brief of some related work, one of the network, which is U-Net, which is like now the go-to network for performing any segmentation tasks, and also some upgrades of U-Net, like attention U-Net or U-Net deep supervision, that's already out there. But we also have an additional problem, like mentioned, that's to deal with small data set, because we don't have such a huge data set of 7 Tesla MRI with high resolution. Later on, I will discuss also about the data set, but to handle the problem of small data set, Botsova et al. Proposed a model of semi-supervised learning, where it was for 2D segmentation of X-ray images, where she combined U-Net with deformation, which is typically used for augmentation, but she used it to learn the consistency between while training, and it was observed that it performed better than just using as augmentation. And she's shown that for smaller data sets, such method works really nice. So our method is also based and inspired by Bostrov et al.'s method, but with a few changes. So first this is the network backbone of our model. And this is an U-Net MSS, so U-Net Multi-Scale Supervision or Deep Supervision. It's a bit different than what has already been done in the earlier work. Like here we are in the contraction path, we are using max pooling instead of strided convolution to go down. And in the expansion path, we are using interpolation with convolution rather than convolutional transpose. And it's called multi-scale supervision because, as you can see, like there are three different levels the losses are calculated. In a typical U-Net, we calculate the loss on the final segmentation output. But in a multi-scale supervision, we also calculate loss for two of the preceding levels. So the level which is here as YL1 and YL2, the output that's coming from those levels, they're interpolated to the original output size, and then the loss is also calculated on those. And then summation of those losses are used as the final loss value. So it's the network backbone. Now,
sorry, I had a question.
Yeah.
What's the intuition behind the benefits of multi-scale supervision?
So when we are having, say, for example, normal U-Net, we are calculating the loss just on the final level. And then when we are back propagating the loss, we are just expecting that in every level, we learn different discriminative features. But with multi-scale supervision, we are enforcing it that they are supposed to learn discriminative features in different levels because they are predicting. So if we look at the image size, they are smaller than the actual size. So we are basically interpolating it to the original size. And then we want to learn features which are like more discriminative in every level. So for every scale of the image, and hence also the gradient flow is better. So this is the main motivation behind going for multi-scale supervision than just simple U-Net.
I see. Thank you.
And maybe I can add something on this.
Mm-hmm.
So like if you think about the vessels, like so you have big ones and small ones, and here like the Y12, it would focus, I think, more on the larger vessels, while the small y, it would focus more on the smaller vessels. That's another way of seeing it. So like the larger the vessel, the more, like because in this downsampled attention map, you lose the information about the small vessels, but you still will be able to supervise on the major outlines of the vessels.
Yeah. Thanks.
Thanks.
So now, but the model or the network backbone is just the center of the whole pipeline or the Siamese architecture, where what we have is we have two branches. So in the first one, what you see in the top half, we have the label, the real label, and the real images. The images are provided to the U-Net, and the loss, the prediction of the U-Net is Y1, and we calculate the loss against the label Y. But now comes deformation consistency learning or deformation-aware learning. What we are doing is we are deforming the input image X to TX and deforming the input level Y to TY. Now, this TX is supplied to the network, and the network predicts Y2 this time, or Y2 cap. And then the loss is calculated, comparing this Y2 and TY. But also on top of that, there is a consistency loss. What's this consistency loss? Is basically we are deforming the prediction Y1, and that's the Y1, and then we have the transformation, and we get a deformed version of Y1. And that is the deformed version of this. We are calculating the consistency loss against the prediction Y cap 2. And this is our consistency loss. So we have two supervised losses. One's coming from the non-deformed or non-transformed image, one coming from the transformed one. And finally, we have the consistency loss. And we are using all these losses together. And this consistency loss is basically here our semi-supervised nature, or the semi-supervised part of the algorithm. And this hypothesis is because we don't have a huge data set from where we're going to learn. We want to showcase different vessels or different vessel structures. And if we imagine the vessels from your brain to my brain, we can kind of see in a deformed way, if we deform them, we can see some similarities. That's the hypothesis. So for that reason, then we are using this as this consistency loss to try to learn from a small data set. Now, what's the small data set that I'm mentioning again and again? So this data set that we are mainly using is a top MRI data set with 300 micrometer resolution. And there are only 11 volumes in the whole data set. And we did a split of 6-3 with 6 for training, 2 for validation, and 3 for testing. And then there was a 3-fold cross validation done. But this is the only data set that we used here. But further, we wanted to test how the performance is, how the generalization capability is. So we also used a public data set, which is ICSI data set, which has MRAs of 450 micrometer resolution, so lower resolution than our training set, and acquired also at lower field strength, so 1.5 Tesla and 3 Tesla MRI. And now comes the labels. The labels were created in a semi-automatic manner using Elastic. So you can see the label, which is the right-hand side image, and you can see how noisy the labels are. We will go into more in detail and you'll see how the labels were imperfect. That was also what we were trying to address here, to address the problem of imperfect labels. So this is what is the training set that we used here.
Can I ask you a quick question?
Yeah.
How big is the ICSI data set?
The ICSI data set is around, I think, 400 volumes or so.
Okay, so what's the motivation for using such a small, I guess, for using the data sets as you did, where the 11 volumes is what you did for the...
Yeah. So the ICSI data set is first of all acquired at 1.5 and 3 Tesla scanners. And the small vessels, like the smallest of the vessels that we are trying to segment, for example, they are not sensitive in those low field MRIs. And they are only sensitive at 7 Tesla. So, or even higher, though for human scans, we just use 7 Tesla for now. And for that reason, if we want to really learn about them, so we are stuck with this really tiny data set of 11 volumes.
I see. Okay.
And also the in-plane resolution is also lower. So it's 300 micrometer, what we have in our data set versus 450 in the ICSI data set.
Makes sense. Thanks.
Yeah. So now the experimental setup. Here, all the trainings were done using 3D patches of 64 cube. The loss was calculated using focal Tarbatsky loss and was optimized using Adam optimizer with a learning rate of 0.01. The models were trained for 50 epochs, but we have observed that all the models converge between 20 to 30 epochs already. To speed up the training and also to increase the amount of patches we can train in one batch, we use mixed precision training that was done using NVIDIA Apex, and the batch size was 20. And for the deformation part, the random elastic deformation was created by modifying the Torch.io's deformation transformation. We modified it and made it a differentiable version, and I also used a 3D B-spline kernel for it, where we had random control points we chose between either 5, 6, or 7. We set the maximum displacement to be 0.02 and locked borders to be 2. We chose these parameters based on our experimentations that we didn't want the vessels to be too much deformed that they don't look realistic anymore. So we did experimentations just to see what kind of level we can do, and then we decided to go with these parameters. For the baseline comparisons, we took 2 kind of, which we can say state-of-the-art methods. One is the traditional Frangi method, which is like mostly used for vessel segmentation, where we also experimented with the parameters to get the best possible that we can get for this data set, where we had a 3-scale Frangi with a correction constant of 0.1 and a final threshold of 0.01. Also, we used the MSFDF pipeline, and we used their official Jupyter notebook, but with one change where they had an offset of 0.2, we set it to 0.0 just to make this also reduce the noise, but also the motivation was because this is supposedly semi-automatic segmentation, not to have any manual offsetting involved in the process. So this was the change from the original implementation. And for our approaches for the deep learning based model, we use U-Net and attention U-Net as our baselines. One more thing I want to mention here is that for Frangi and MSFDF, there were two pre-processing steps involved. So all the brains were, the volumes were brain extracted, so only the brains were supplied, and also a bias field correction was applied. In 7 Tesla, this problem of inhomogeneity is quite prominent. So this bias field correction was done to improve the results. However, for the deep learning models, baselines for our models, there were no such pre-processings involved. So only the data that we got from the scanner was directly supplied for training or for inference.
Can I ask another quick question?
Yeah.
So why not apply the bias field correction for the deep learning inputs?
The main idea was in this case, we wanted to reduce the pre-processing steps. So we wanted to just keep the raw data that we get from the scanner and try to use that. Because also personally, I have some future plan of extending it with reconstruction. So there, we want to have reconstruction model followed by segmentation model. In those cases, it will become more complicated. And so we have just a simple raw that we had. So there were some experiments done also with bias field correction, but there were no thorough experiments. There were no cross-validation, just some small experiments. And there were no improvement done when we use bias field corrected data. So then we decided not to go ahead with that.
And then for your baselines, your deep learning baselines, did you have baselines of other methods that were developed specifically to handle small amounts of labeled data?
No, just a typical U-Net or attention U-Net.
Okay,
So,
got it.
Yeah. So they were not meant for small data sets. However, they're not learning just 6 because we are doing the patch-based training. So they were like 8,000 patches in every epoch. So from that perspective, it's not really small, just the small in terms of the variance because just 6 updates.
Okay. Thanks.
Now coming to the results. So just for a qualitative check, on the left hand, we have the non-deep learning results and also the locations from where we got these ROIs. And on the right, we have the deep learning results. For Frangi, we see that it's not so noisy, but we also lose a lot of vessels. The red means under segmentation, so the things which were there in the label, but were not segmented. And in the MSFDF, we see it better in terms of having number of vessels, but also it's more noisy. However, I want to mention one thing. These are all comparisons done against the elastic labels. So elastic labels are also noisy labels. So even these comparisons aren't totally perfect. And but this is for the deep learning models, they were kind of all of them had more or less similar results. But maybe in some cases we see U-Net to be predicting a bit more noisy result compared to the other ones. But moreover, there were not so much difference noticed here. But I will come to some other experiments to show the difference in a better way. But also to see in a quantitative analysis using DICE and IOU, we can see the Frangi, which is the best non-deep learning baseline here, got a DICE coefficient of 52% approx, whereas U-Net, which got the least DICE here, still got 76%. And then the U-Net MSS, which the model we are proposing here, got 79.35. U-Net with deformation, so the U-Net with deformation as in Bostova et al.'s proposed method, just in a 3 version now, achieved 79.44. And our U-Net MSS with deformation got 80.44. Also, we ran statistical analysis and we saw that both U-Net plus deformation and U-Net MSS plus deformation got significant improvement statistically compared against the models without deformation. And also comparing attention unit as well. So U-Net MSS plus deformation got significant improvement. Also, U-Net MSS got significant improvement over U-Net, simple U-Net. But there was one thing that U-Net MSS plus deformation did not get any significant improvement against U-Net plus deformation. Now, as the data set of labels that we saw, they were noisy. So now we are looking at some manual segmentation. So we have, because it's like really tiny vessels we are trying to segment, it was not done on the whole volume, but on a small ROI to check how the performance is. So here you can see the input, the manual segmentation, followed by the U-Net results and all the other results. And if you notice in the center, this opposite Y figure there in the center of the image, you can see the deformation models. They maintain the continuity far better than the models without deformation. And if we compare against the MSFDF, which you can see still maintain the continuity really well, but the result is also super noisy. Now, if we compare the elastic, which is basically our training labels, so same as training labels, you see that even elastic had not this Y shape continued properly. So the U-Net deformation or U-Net MSS deformation, it could predict these continuity, even though the ground truth had this continuity missing, but still it could learn and could predict and consider this as noise. So we can see here in this example that how the deformation-based models performed way better than the models without deformation. And we also did a quantitative evaluation using DICE. And here we can, first of all, the thing we should see is the training label, which is elastic, which only had a 50% DICE compared against this manual result. And now when we see the other models, so we have U-Net, which had 47, compared to the U-Net deformation, which got almost 60, and U-Net MSS deformation got 62.07. For the non-deep learning baselines, also Frangi got 57.59 and MSFDF got 52.39. So these were the results comparing against manual segmentation. Now we did also an experiment because we are thinking of small data set. The question was, how low can we go? Like the effect of the training set size on the results. So we reduced the training set size, which all the experiments done with training set size of 6. And now we kept on reducing it to 1. So 1, 2, 4, and 6. And here we can see the orange ones are with deformation and the blue ones are without. In every case, the ones with deformation performed better than the ones without. Though the variance, it's kind of, it increased a bit. But one thing to notice here is when we are training just with one volume, still it got an average type of size of like 0.74. So this also gives us an intuition that we can do something like this, maybe that we can create a perfect ground truth for one volume and use that to train or fine-tune the model to improve the results even further. And this is the result for U-Net and U-Net MSS in left and right respectively. Now testing it for generalizability. So as we said that we trained it on 7 Tesla data, but how is the performance on 3 Tesla data or 1.5 Tesla data? One thing I want to note first is that these data were not so much inhomogeneous like 7 Tesla. For 3 or 1.5 Tesla data, we don't need bias field correction so much. So in these cases, that can already have a negative impact because the training was done with this inhomogeneous kind of data, but the inference was with this homogeneous distribution of data. Here you can see also that if you look at the center again, you can see the deformation models, they maintain the continuity better compared to the ones without. But now what is this PS64 or PS96? It's basically the path size. We have this idea that because the resolution is different, we wanted to experiment with the path size. So we reduced the path size to 32. So the training was all with the same training, so 64. but the inference was done with 64, but also with 32 and 96. And what we noticed was by increasing the path size to 96, we got better results than 64. But one thing from the intuition perspective, our intuition was that the 32 would perform better because that will have similar coverage in terms of the volumetric coverage because of the resolution. But it wasn't the case. We have seen the 96 perform better. So of course, we need to do further experiments to see the reason behind it and also the effect of the bias field. So maybe if we train with bias field correction, this might improve in this case. There's one final additional experiment I want to point out, and that is with artifacts. The networks were trained without any kind of artifacts, with just the input images, the raw volumes. Then we supplied different kinds of artifacts, some MR artifacts like spikes, motion, and other artifacts. And we wanted to see how the performance is after supplying these artifacts. And here, surprisingly, the U-Net MSS without deformation performed quite well compared to the one with deformation. So this was, but also if we say U-Net is not one of the best ones, so U-Net MSS is the best, as we can see in almost every case, actually for every case, and between among all the different artifacts, for random spikes, all the models failed. So the best is U-Net, but a dice of 8. So we can say that this failed for everything. So this is something one to note. So, but random spike in the image means it's a significant problem with the scanner. So it's maybe not so so much we are going to be encountering. But things like random noise or motion or random bias field, these things are something we can encounter on a daily basis. So we can see the models performed quite decently for bias field or noise. And but yes, U-Net MSS was the one which performed best. But we want to do further experiments to see how this affects and what is the reason behind it. So now to conclude, the proposed method we saw just now outperformed all the baseline methods significantly, and the models with consistency, deformation consistency perform better. And we were even be able to segment with the dice of 0.74 when we are just training with one volume, and the deformation-aware models could maintain the vessel continuities better. Now for some future work that we planned for this project, one is to use these artifacts that we just seen as data augmentation. So that can help the model to be robust against these artifacts. And also mixed training with different resolutions or in different field strengths. So 150, 300, 450 micrometer resolution and 1.53 and 7 Tesla field strengths. If we mix in the training, that might make the model more generalizable, and then it might be able to handle all different kinds of resolution better. And one more idea that we have seen in some cases, the vessel continuity were not perfect. So we would like to incorporate the maximum intensity projection as an additional loss term to have better continuity for vessels. And this code is publicly available on my GitHub, so you can have a look. And finally, thank you so much for your attention. If you have any questions, feedback, you're most welcome.
Thank you. Very nice. So we have like a few minutes for question, and remember it's like live.
I'll ask another quick question if that's okay. So you focused on this one application of brain MRs. I'm curious if you think that the losses that you incorporated here that you saw to perform better than the U-Net and the attention U-Net would also perform better in other segmentation tasks, or if the losses being used are kind of particular to the different resolutions of veins that you see and are trying to segment specifically in brain MR.
So I have tried U-Net MSS or the particular loss function also in other tasks, not in this semi-supervised setup, but in general. And I've always observed in most cases that U-Net MSS performs better than U-Net. And attention U-Net sometimes even performs worse than U-Net, sometimes maybe similar, not something I noticed something significantly different. But U-Net MSS in general, I've always observed it to perform better. And in terms of loss function, this was also one of our observations that focal Chauvet-Sky loss works better than dice loss, is typically what we use for training. But focal Chauvet-Sky gave better results also for other tasks like abdominal segmentation, where first time we used this loss function for our works were for chaos challenge, which is one of our other paper you can have a look, and that was for abdominal segmentation.
Okay, cool. Thanks.
Welcome.
Did you compare like to other losses that have, like that try to take into account imbalance in the data set?
No, here there was just comparison with dice. There was one comparison done, but again, like preliminary experiments, not with cross-validation, just initial experiments. And focal Chauvet-Sky gave better results. So then from that on, we just kept this.
Okay. Okay, so if there are no other questions.
Oh, I have one more question. I saw
Okay.
you did the 3D patches.
Yes.
Did you try 2D? Did 3D work significantly better?
In this case, because if we look from 2D perspective, they're just kind of points everywhere.
Oh, okay.
Because it's just vessels. When we are looking in 3D, then we see the whole the vessels properly. So for that reason, we thought like maybe a 3D approach would be better or make more sense in this case. So no, I haven't tried with 2D in this.
That makes sense.
Okay. So I'm trying to thank you very much, Soumick.
Thanks for having me.
You're welcome. I'm trying to find I'm always having problems